Yes.
Yeah.
Yes.
Yes? Really?
Some teachers think that it's like their intellectual property, quote unquote.
Well, okay, first of all, I'm not intellectual, so. And two, I have no property. So, do whatever you want with it. Okay, so let's see. Auto setup. Just want to make sure that it is maximized, because occasionally it's cutting off the left edge just a little bit. It's not. Do that one more time. Switch. And auto setup. It's not doing the auto setup. Okay, but it's still visible. It's fine. Okay. So I'm gonna unzip double1.zip again, just like usual. Go to the folder and then look at the function. There we go. Okay, so I think what I want to do is to explain the approach first. Okay, why we need to do the things that we need to do, and why do we need to do it in the order that we need to do it in the order of. Okay, so the first thing we need to do is to structure the outer loop, because what is the objective of your homework assignment? You want to turn the exp10 to 0, right? You want to change it to 0 so that the number is no longer expressed as the quantity of some powers of 10. We only want to express it as some quantity of powers of 2. That is the objective. Is that okay? So that means it makes sense, okay? Now how long it takes to get to understand that this is the loop, that's a different question. But basically we want to stay in the loop as long as exp10 is less than 0. Okay, because in the first homework assignment, the one that's due on Tuesday, the given test code that you have to deal with, they all have negative exponents. Okay, so this makes sense. Now, when we look at a loop, okay, this is not assembly language programming, but in general programming. If you can determine the condition of a loop, you already know what the loop is going to have to do. Okay, at least a little bit. Because in this particular case, if I stay in the loop as long as exp10 as a member is less than 0, that means something in the loop is going to increase it. Okay, so that eventually it becomes 0. Does that make sense? Okay, so that means the code to do the division by 10 and also to increment exp10 really should belong to this outer loop, not in the inner loop. Okay, so we will say, okay, so let's do that. Okay, Mantissa is Mantissa plus 5, and this is why I do not like infix notation, because I have to go back and use parentheses. Okay, plus 5 and divide by 10. Okay, so now we have to ask the question, why are we adding 5 before dividing by 10? Why? What happens when I don't do the plus 5 and then division by 10? Right, so this is taking the place of rounding, but what happens when I do not do rounding and instead I just do floor? What is the difference that it's going to make?
More error.
It's related to precision, but it's not the precision itself. It has to do with
Error.
the error, but what about the error? We always have error.
More error.
It's more error because
It's all leaning to one side.
exactly, it's all leaning to one side. So if we do not do the plus 5, which is implementing the rounding function, but only using integer arithmetics, then when you err, you're always erring on the smaller side. Okay, the result of the division is always going to be smaller than what it is supposed to be. Now, there's no way to represent the exact result, okay, of this division by 10, but you want the error to sometimes err on the larger side, other times err on the smaller side, so that it's not biased. Without the plus 5, it is going to be biased, which means the effect of erring on the smaller side is cumulative. So by the time you're all done with all the iterations, your actual result will be significantly smaller than what it is supposed to be. as opposed to when you do rounding, it's still not going to be exactly the same, but it's going to be much closer because you don't have a biased error. Okay, very good. But before this, we also have something else to do, because in the notes, I kind of emphasized that we want to maximize the value of mantissa before we divide it by 10. Why are we doing it? The why is more important than how we're going to do it. So why are we trying to maximize the value of the mantissa before we do the +5 and division by 10? So you think about 23 divided by 10, okay? Integer division. What is 23 divided by 10 when we have integer division? 2. What is the error? The percentage of error. It's 0.3 out of 2, which is, what, 15%? Something like that. 15% doesn't sound like a lot until you think about, you go to McDonald's, okay, and the change is supposed to be $7.11, and then the person behind the counter says, here's $6. Where's the rest? $6 is close enough. So then you start to think about, oh, maybe 15% is not acceptable, right? Okay. So how do you minimize the error? You make the numerator larger and larger and larger, right? So tell me, what is the error when you divide 203 by 10? What is the percentage of the error? It is 0.3 out of 20, right? So it's now 1.5%. What about 2003 divided by 10? 0.15%, okay? So as you increase the number, even though you still have an error, but the percentage of the error versus what the number is going to be smaller and smaller. And that is why we want to maximize the mantissa so that it fills up the entire 64-bit number before we divide it by 10. Is that okay? So the rationale is important. It is almost more important than the mechanism to make it happen. Okay, so what is the largest value that we should make it? I'm going to use a const up here to define that. So I'm going to say const uin64 underscore t. We'll call this max1. What do you think that should be? In other words, when the mantissa is at least this much, we should stop. We should not be doubling it anymore.
Make it 1 bit and bit shifted left 63 spaces.
That would not take into account of the +5. Okay, so let's look at that number first. Okay, so let's look at this one, which is 8 followed by 15 zeros. Okay, so I can do this 15. Oops. Okay, 15A0 escape. There we go. Okay, so let's say we use this particular max here, and then we say while Pn points to mantissa is less than max1, then what we do is we double mantissa because we can play with the power of 2, okay? So we can multiply equals to 2 or left shift once, either way works. And then we adjust exp2 by decrementing it, okay? Decrement Pn points to exp2. Okay, so this approach looks like it should work, right? Because when mantissa is greater than or equal to this amount, we should stop, right? There's only one little problem with this approach. What is the very last value that will still, that will still make this condition true? What is the value of the mantissa that will still make this condition true? It will be 7 with all the f's except for the last one. It's going to be an f, right? 7 f, it's going to make it. It will still make this condition true. So what do you get when you double 7 followed by all f's? You get all f's except for the least significant digit. It's going to be an e, right? So that means you are only one value away from overflowing the largest value of a 64-bit integer. And then you look at what we do to the mantissa. we're adding 5. In other words, if we use this approach, there are very few cases where by the time you get here, the add 5 is going to overflow the largest value of a 64-bit number. Okay, so that's why we are off by just a little bit. So I'm going to adjust max 1. So instead of doing it this way, I'm going to say, let's make this all F. Okay, and then we'll minus 5 from that, because that's what we're going to do when we exit the loop, and then we divide it by 2. Now, the actual value of this one compared to what we had before is only off by like 2 values. Okay, it's not by much, but it does make that conceptual difference that this one will never fail as opposed to the other one, which is kind of like, if you're really, really unlucky, there's one case where it doesn't work. So if your software goes onto a space shuttle or a Mars probe, that can turn out to be expensive. Or SpaceX these days. Is anyone planning or inspiring to work for SpaceX or something like that?
That'd be cool.
That would be absolutely cool.
Just float in space for a little.
All right, so we're going to keep it this way, and by the time you get out of the loop, there's one little thing you have to do, because the very last thing that you're going to do before you exit the loop is the division by 10, which means on this line, Mantissa is already as big as it possibly can, but right after the division by 10, it's no longer as big as it possibly can. So now you have to just kind of bump it up again. But when you bump it up again, you're not going to use the same loop as the other one, because you don't have to worry about the plus 5 anymore. So this time it really is just Mantissa, and I'm going to use this approach and see whether you guys can make sense of this. Okay, and I'll explain that in a moment. Give me a second here. I'm changing the way I do things just to illustrate that they mean exactly the same thing. There we go. Okay. Can everybody see how this loop? Oh, okay. I forgot a negation. So let me make a negation here. There we go. Okay. And we'll turn on line numbers just so that I can name a line. There we go. So on line 23, what is it saying? When do I stay in the loop? Well, the first thing you notice is there's a negation, right? So it's a negation of some expression. So what is it negating? It's negating Pn points to Mantissa right shift 63 times.
Getting on the most significant bit.
Is turning the most significant bit into the least significant bit. Bit 63 becomes bit 1. Oh, if bit 63 becomes bit 0, sorry. Okay, bit 63 becomes bit 0, which is the least significant bit. What about the other bits? What about the original bit 62? Where is it now? It's shifted out of the integer. In other words, I'm throwing away 63 bits. Okay, the least significant 63 bits are now thrown away. I'm moving the most significant bit, bit 63, to bit 0. So the result of this expression can only be a 1 or a 0. It cannot be anything else. If it's a 1, it means the most significant bit is a 1. If it's a 0, it means the most significant bit is a 0, which also means, we need to bump it up a little bit. Line 17 and line 23 are basically doing exactly the same thing. One is being done using multiplication by 2, and the other one is being done by a left shift by 1. But they mean exactly the same thing. Is that okay? Now, I understand that this is not something that is in quote-unquote assembly language programming, but by this time, I really think that you guys should start to understand how line 17 and line 25 are really the same thing, or how line 23 is going to get the job done by saying, oh, as long as bit 63 is not a 1, let's keep doing this. Now, if at first glance you don't quite understand it, you have to spend some time to try to understand it, because this is C programming. I mean, which is the prerequisite of this class. So with some looking up, some research, and some reading, I'm hoping that you guys will actually get to understand this code. Question? Yes?
Can we just talk about max 1 for a second there?
Yes.
And the value that you set it to.
Mm-hmm.
What is that value again?
Okay, so with this one, I have one little mistake here. That should be less than or equal to. Okay. So think about this. What happens when Mantissa does equal to max 1? We have one more iteration to go, right? So what does it mean when we go for that next iteration? When Mantissa is exactly this amount, what do you think is going to happen? The Mantissa will be doubled, right?
Oh, we're going to reach...
Then it becomes all f's minus 5.
Yeah.
And then we are going to add 5 back to it. So when we add 5 back to it, it will still be up to just the largest integer that we can represent using unsigned integers. We make sure that there's enough room for the add 5.
Okay.
Plus 5. Is that okay?
And how come we don't... Okay, and the reason we don't have to do it in the second while loop is because we're not going to be doing rounding. We're just making sure
Correct.
bit 63.
Yep, exactly. In the second loop, we are not doing rounding because there are no divisions. When there are no divisions, there's no need to do rounding. Multiplication does not need rounding. It's only the divisions that we need rounding for.
Okay.
Yep. So are we relatively comfortable with this code? Are there any particular lines that you want me to explain? Because now would be a good time to ask.
Just fill up the just a second.
I can do better. And I think we are recording, so there's no need to try to copy everything, because that would not be a good use of your time. Yep, we're recording. So are we good? Yep.
In your notes, you mentioned that
There's a plus 5 instead of a minus 5.
no, oh, never mind, changed it. Okay, never mind.
Okay.
Yeah, I know about that one, but you had originally had just the less than, and in the notes you said less than or equal to.
Okay. Yep. So is that okay? All right. Okay, so with this one out of the way, and well, let's run it, okay, because I don't trust myself. Neither should you. When I said that, I meant it in both ways. You should not trust me, Tech, nor should you trust yourself, you. Always question, always be skeptical. And be skeptical about skepticism itself. Recursive. Be skeptical recursively.
You might like run out of memory at some point.
Stack space, yes. Stack overflow. Underflow, actually. Okay, you guys will understand why the stack does not overflow. It actually underflows. We'll get to that point. Okay, so we'll compile the code, the program, gcc-g-o main.c, exp1022.c, and parse.c. There we go, gdb main. And if I'm confident enough, I'm going to put a breakpoint on the return 0 line, and then run it with, let's see, what should I run it with? 0.125, which is an eighth, okay? And print n. Okay, so this doesn't really tell you a whole lot. Okay, let me move this up a little bit. This is the reason why I shrunk the window, because people in the back may have a hard time actually seeing the bottom part of the screen. There we go. So I can print it in hexadecimal. This makes more sense, because now we can see how the Mantissa is actually just 1 in binary. It's just 1 followed by 63 zeros. Because in 1 hexadecimal digit is equivalent to 4 bits. So you basically just have to look up the definition of, oh, what is 8 in binary, what is 0 in binary, and so on. So the more important part is the exponent of 2 is negative 66. So we have the mantissa being 2 to the power of 63 times 2 to the power of negative 66. What do you get? You get 2 to the power of negative 3, which is 1/8, which is 0.125. So I got back the original value. And at the same time, I also make sure that bit 63 is in fact a 1 when I look at the hexadecimal representation. It's much harder to look at the decimal representation to know whether bit 63 is on or not, but when you look at the hexadecimal representation, it's a little bit easier. The other way is to use the same trick that I used earlier, which is n dot mantissa, right shift 63 times, and you can see that it is a 1. Okay, so that's the other confirmation that we have bit 63 being a 1. All right, so are we cool with this solution or not? We good? Okay. All right, so moving on to the new homework assignment. So the new homework assignment is not really that new, okay, because you know most of you probably anticipated the homework assignment already. So we'll go to, oh, this is the wrong thing. This is for the Design Hub. Too many tabs. All right, so this is your new homework assignment. It is positive exponent. So last time we dealt with negative exponent, now we deal with positive exponent. So when you look at the description of the homework assignment, it's almost identical to the one that you have dealt with already. The first link has changed, by the way. So when you click on this link, it will take you to the spreadsheet that has a positive exponent instead of a negative exponent. So make sure that you update the number that you're going to use to test your program. Is that okay? All right. Now, getting back to here. But I'm including something else to help you debug your program. I'm including a trace of how the values change when I process 1.2345678 E30. Okay, so when this number is first parsed, the first time I get into my program, the parser, okay, this is too big. One more. There we go. So the parser automatically turned the mantissa into 1.2345678, losing the decimal point. But since I'm losing the decimal point, I have to adjust the exponent of 10 to account for shifting the decimal point 8 times to the right-hand side. So that's why EXP10 is now 22 instead of 30. Question?
Is that something we have to do, or is it?
No, you don't have to do this. The parser takes care of this part.
Oh, okay.
Yeah. Okay, so these two lines are the same because they're basically printing from different parts of the program, and it turns out that is the same thing. So now we look into the first change that is happening to mantissa. So we are looking between these two lines. What changed between these two lines? Look at the mantissa. Look at the exponent of 10. They're changed, right? So I'm already maxing out the mantissa. This is as far as I can multiply 10 to the mantissa before it overflows the value of a 64-bit unsigned integer. I can no longer multiply 10 to the mantissa anymore at this point. Is that okay? So what do I need to do? So what happens between these two lines? You can see the mantissa is changed quite a bit. In fact, it's approximately 120 divided by 15. That's the magnitude of the change. And that turns out to be, guess what? About 8. Okay? So the mantissa is about 1/8 of what it used to be. So what else got changed between these two lines? EXP2 got changed, right? So you can see how EXP2 was a 0, now it is a 3, which is equivalent to multiplying by 8, which makes sense because the mantissa is 1/8 of what it used to be, but the exponent of 2 is taking care of that by increasing the exponent by 3. Is that okay? So this is how I make room in the mantissa for the next multiplication by 10. I basically keep dividing it by 2 until it is less than the maximum value of a 64-bit number divided by 10. Then I have the room to multiply by 10 again, and that's why between these two lines, the mantissa is now 10 times more than what it used to be, and then exp10 is now 1 less than what it used to be. Because when I multiply the mantissa by 10, in order to preserve the value represented, I have to decrement exp10. Is that making any sense? Okay, yep.
There's no rounding thing we're worried about here with this one.
You do have to be careful. Yeah, when you divide by 2, you have to deal with rounding.
So the +5 again.
No.
Plus 1.
Oh, +1, yeah.
Yep, you add 1/2 of your denominator before you divide it. Yep. Okay, so from here to here, I think you guys know what has happened already. I have approximately 15 blah blah blah, and I end up with 9.6 blah blah blah. So what happened here? There's a division by 16. Very good. So there's a division by 16. The mantissa is now divided by 16, but in order to preserve the value that I'm representing, you can see how the exponent of 2 is now increased by 4 to account for the division by 16. So the division by 16 is here so that I can make room for another multiplication by 10. So between these two lines, we have the multiplication by 10. And after I did the multiplication by 10, this number here is as large as it possibly can be before I overflow a 64-bit unsigned integer. Is that okay? So from here on, it really is just alternating between these two processes. Okay? Keep dividing it by 2 until we have room for another multiplication by 10, multiply by 10, and then go back and make room for another multiplication by 10, and so on. Do we have any questions about this alternation of processes? Yep.
So it's going all the way up to where we have 1 multiplication by 10 left, and then it's multiplying by 2 while it is less than.
There's no multiplication by 2. There's only division by 2. Yeah. So in this particular scenario, because we're trying to change a positive exponent of 10 to 0, so we are multiplying by 10, but we are dividing by 2. The division by 2 is to make room for multiplication by 10 from the perspective of the mantissa. But every time we multiply by 10, we have to adjust the exponent of 10. We have to decrease it by 1. And then every time we divide it by 2, we have to increase the exponent of 2 because we want to preserve the value represented.
So for the loop where we're going up by multiples of 10, we're doing that just while the mantissa is less
There
than.
are several ways to do it. So how you want to structure your code is up to you.
No, it's not regarding code. Just the comparison number is just
Oh,
the
okay.
highest 64 int.
So you're talking about how far we can multiply by 10 before it's overflowing?
Yeah, so we're just gonna do it while it's less than the highest 64 int.
Divided by 10. Yeah,
Okay.
you have to stop before it overflows.
And then the same thing we're gonna do with the 2 though, except
The division by 2, you don't have to worry. So the division by 2, you have to basically say, does the mantissa have room for another multiplication by 10?
Okay.
Yep.
That's what I thought. Okay.
Yep. So you have to compare to the largest possible value in 64-bit divided by 10.
Yep.
If the mantissa is less than or equal to that, then you're good, right?
Yeah.
All right. So is this helping? Because in the previous assignment I didn't give you a sequence like this, but this time, I'm giving a sequence like this. But I do have to emphasize, huh?
It helps a lot.
Helps a lot. Okay, cool. But I do have to emphasize that between lines like this, there's actually a loop here. Okay, because exp2 does not just change from 23 to 26 in an instant. It actually goes through an inner loop to go through 3 times. Basically, it needs to keep dividing by 2 until there's enough room. Okay, so I just want to emphasize that it's not like one line per iteration. Some of these lines represent multiple iterations of an inner loop. Is that okay? So are we kind of confident we can get it done in a week? Okay, cool. So I will leave it up to you guys to work on this. I'm gonna stop the recorder unless somebody has a question about the code. Are there any questions? No questions?
About the previous one?
Uh-huh.
For the subtract, is it with that code, like for the answer, you were expecting us to put the mantissa that you have there and the exponent, exponent in the binary exponent that you have represented there. So basically, copy paste in there, right?
Yeah, you just copy and paste.
Okay.
You can use the hexadecimal representation, you can use the base 10 representation, either way works. Yeah, especially if you're just copy and pasting from GDB or the GDB prompt in code blocks, that's fine, that's more than sufficient. Okay, any other questions? All right, if there are no other questions, I'm gonna stop the recording. And there we go.